In today's video, I will discuss how to construct proofs. Of course, every proof is different. In general, there is not a strict set of steps one can follow to construct proofs. However, there are still some general strategies that can be beneficial. I chose this problem to highlight some of the challenges as well as strategies when it comes to proof writing. Because often what you see in the final proof, in for example a solution manual, is only the tip of the iceberg. Often there are hidden work and exploratory steps that are not presented in the final proof, but is still instrumental for constructing the proof. So let's begin. The problem asks to verify, using the definition of the convergence of a sequence, that the following sequence converge to the proposed limit. To do so, let's first recall the definition of convergence of a sequence. And here it is, which is sometimes referred to as the epsilon big N definition. It says let an be a sequence in R and L be a real number. By an converges to L, or L is the limit of an, we mean that for every epsilon greater than 0, there exists a big N, that is a natural number, such that for every natural number little n, with n greater or equal to big N, the absolute value of a little n minus L, which is the distance between an and L, is less than epsilon. If this is true, we write xn converges to L, or equivalently, the limit of xn is equal to L. If you're unfamiliar with this definition, which is arguably quite involved, you can go to one of my previous videos called This is Mathematics. The exact timestamp which I explain this definition can be found in the video description. Let's look at some of the main ideas for constructing a epsilon big N style proof. And here they are. And before we write down the final proof, here are some of the baby steps that can be helpful. First, lay out the main structure of the proofs. Left blanks where needed. The main structure of the proof is informed by the definition of limit. And speaking of which, the main idea from the definition is to make the distance between an and L small. To make this happen, usually we'll simplify the distance expression as much as possible. And then going back to the main structure of the proof, which we laid out earlier, we want to fill in the specifics. And this is generally the hardest part. And we'll get back to the last point a bit later. We first write the main structure, which you can think of as a template. Because the definition says for every epsilon greater than 0, there exists n blah blah blah. So let's write let epsilon greater than 0. That's our first sentence. And then we write pick big N dot dot dot. The dot stands for the specifics to fill up later. And then the definition continues and says this big N has a certain property. That is, for every little n greater or equal to big N, we have a little n minus L less than epsilon. So we wish to demonstrate that is true for our specific choice of n. And therefore we write, suppose little n is greater or equal to big N. Then we leave more blanks, which stands for the detailed deduction that shows when little n is greater or equal to big N, the absolute value of an minus L is indeed less than epsilon. So this completes our main structure. So now let's go to the first limit that we want to prove. As mentioned, we want to simplify as much as possible the absolute value of an minus L. We simplified the distance between the general term in the sequence and the proposed limit. And the result is 3 over 5 times 5n plus 4. The goal is to make the distance small. So obviously we want to make n large. But how large does n needs to be? We want the distance to be less than epsilon. So now it's time for some rough work. We want the distance to be less than epsilon. And epsilon is a given arbitrary number. We know that intuitively when n gets larger, this fraction gets smaller. We can then rearrange the inequality and solve for a condition on n. And then subtract 4 on both sides. And then divide by 5 on both sides. And this is our condition on n. And since the result of every transformation we just performed is equivalent to the original inequality, we have the criteria for n. And we're just going to call this big N. And there's a little technicality. The left-hand side might not be an integer. So we just pick n to be an integer greater than the left-hand side. And we're good to go. We're now ready to write the formal proof. We'll first copy the template. We can continue the sentence, pick n to be an integer such that big N is greater than the threshold we just found in our rough work. So far, we did some algebra, simplified the distance between an and the proposed limit, and then we let epsilon to arbitrary positive number. We managed to pick an integer big N for such arbitrary epsilon. And now it is left to show that for every n greater or equal to big N, an minus L is indeed less than epsilon. We'll just plug in an and L into the final inequality to get our final step of the deduction. And we write then, followed by the result of our previous simplification. And since little n is greater or equal to big N, the simplified fraction on the right-hand side is less than or equal to the same fraction, with little n being replaced by big N. And since big N is greater than the threshold we defined earlier, now the right-hand side with big N is less than the same fraction, but with big N replaced by the threshold. We can then simplify the numerator, which is just equal to epsilon. And at this point, the proof is pretty much finished. We pick an arbitrary epsilon, selected an n, and show that for every n greater or equal to big N, the distance between the sequence term an and the limit L is less than epsilon, which is exactly what the definition of limits demand. We'll just add a final concluding sentence to finish the proof, or maybe break the lines in this deduction to make things look nicer. And here's the final concluding sentence. By the definition of limits, or by the definition of convergence, the limit is 2 over 5. And we add the square symbol at the end to signify the end of the proof. What we just wrote is very similar to what is typically found in a solution manual. For a beginner reading such solutions, the choice of big N may seem bewildering. This is because typically proofs are not written in a linear manner. That is, from the first line all the way to the last line. Some kind of exploration of rough work is typically done on the scrap paper and is not presented in the final form. This can be frustrating for learners, but that is simply the standard of proof writing. The purpose of the proof is to convince the reader with absolute certainty that the result is true. It is not the purpose of the proof to teach the reader how to come up with such a proof. That is the job of instructors or YouTubers like me. So going back to how we solved this problem, we started from the inequality that we wanted, and then isolated n, which is essentially solving an inequality. But sometimes solving the final inequality that we wanted directly can be very messy or downright impossible, which brings us to the final main idea that I skipped earlier. Sometimes solving the inequality, the absolute value of an minus L less than epsilon, is messy or near impossible, in which case we should look for an upper bound for an minus L instead. Because in the definition it says for every n with n greater or equal to big N, an minus L absolute value is less than epsilon. This means that the condition little n greater or equal to big N only needs to be a sufficient condition for the absolute value of an minus L less than epsilon. It does not have to be a sufficient and necessary condition. If we manage to find an upper bound of the size of an minus L, and if the upper bound is less than epsilon, we know that an minus L absolute value has to be less than epsilon. Hopefully, the upper bound will be easier to work with. That is, it is easier to solve the inequality upper bound less than epsilon. And that is exactly the strategy we're going to use for part B and part C. The goal now is to prove this sequence 2n squared divided by n cubed plus 3 converges to 0. As usual, we bring down the template. Let's first start by writing down the distance between the sequence and the proposed limit. There's not much to simplify because the sequence is positive. So now what we want we want the distance to be less than epsilon. That is, we want 2n squared divided by n cubed plus 3 to be less than epsilon. But directly solving this inequality is messy because of the cubic term. So instead, we consider deriving an upper bound for the distance. So we write in the beginning of our proof, we start by deriving an upper bound. An easy way to obtain an upper bound is simply getting rid of the 3 on the denominator. This way, the denominator gets smaller and the fraction gets bigger. So this is less than or equal to 2n squared divided by n cubed. And this is of course 2 over n. So now we can just pick n large enough so that the upper bound is less than epsilon, in which case the distance itself must be also less than epsilon. Let's get back to the scrap paper. The upper bound is 2 over n. We want the upper bound to be less than epsilon. And this is extremely easy to solve, which is just n greater than 2 over epsilon. And this is basically the choice of big N. We just pick big N to be greater than 2 over epsilon. We're ready to write the formal proof. So we write pick big N to be an integer such that n is greater than 2 over epsilon. Following the template, suppose n greater or equal to big N, we write then, copy down the upper bound. Since little n is greater or equal to big N, 2 over n is less than or equal to 2 over big N. And since n is greater than 2 over epsilon, 2 over n is less than 2 over epsilon. And of course, it's just epsilon. Add a concluding sentence to finish the proof. As you can see, the second result we just proved hinges on this upper bound. This is the most important step in our proof. And in fact, in many areas of applied mathematics, searching for all kinds of upper and lower bounds constitutes a huge part of research. Just to give you an idea of what I'm talking about, I'll make a brief detour and we'll come back to part C of the problem. For example, in practice, differential equations are often solved by numerical methods. The most basic version is called Euler's method. The idea is to use a finite sequence of polygon lines joining end to end to approximate a smooth curve. But how do we know this method works? How do we know this gives us a reasonable approximation? And here we have the theorem that says Euler's method is convergent, meaning that if the step size of the polygon lines are small enough, the approximate solution gets arbitrarily close to the exact solution. And to prove it, we first define the numerical error. That is the difference between the approximate solution and the exact solution. Then we obtain an inequality, the upper bound of the size of the error. And from this error estimate, when the step size h goes to 0, the error goes to 0, and therefore Euler's method is convergent. As for the part C of the problem, the last limit, let's first think about how we're going to approach this. First, as usual, we compute the distance between the sequence and the proposed limit. So this is just going to be the absolute value of the sine of n squared over the cube root of n. And we want that distance to be less than epsilon. Because of the sine term, it is impossible to solve the inequality for n. But since the absolute value of sine is less than or equal to 1, we have a natural upper bound. So let's write that up. As we did earlier, we first lay out the template. As we just discussed, we derive an upper bound first. The distance between the sequence and the proposed limit 0 is less than or equal to 1 over the cube root of n. Going back to our scrap paper, we want the upper bound to be less than epsilon. And we can easily solve for n. So we're going to pick big N to be greater than 1 over epsilon cubed. Let's write the formal proof. Now suppose little n is greater or equal to big N, then copy down this upper bound. We have that the upper bound is less than or equal to 1 over the cube root of big N. And since big N is greater than 1 over epsilon cubed, the right-hand side is less than epsilon. And this marks the end of our proof. So yeah, that's the end of today's video. Let me know if you find this type of content helpful, not only working out a proof, but also showing the motivation and rough work that goes behind proofs. Thank you very much for watching, and I'll see you next time. Bye.